This tutorial introduces composite slab types and their structural behavior. It covers slab geometry, material settings, and construction stage configurations. Shear stud placement, load definitions, and boundary modeling are explained step by step. The video concludes with creating and modifying slab openings. A complete, code-compliant composite slab model is achieved by the end. Now let's move on to the Steel Slab command. Under the Steel Slab tab, you'll also find the Composite Slab command. I'll click on it once. In the window that opens, you'll see the available floor slab options and their details. Let's begin with the settings on the far right. Starting with the General tab, we see 4 slab types. 2 of them are composite slabs, trapezoidal and solid composite, followed by concrete and lastly, metal slabs. The concrete option refers to a standard reinforced concrete slab that doesn't interact structurally with steel and simply transfers loads and acts as a diaphragm. The metal slab on the far right represents thin metal sheeting, typically 3 to 4 mm thick, commonly used in industrial structures where only equipment or maintenance access is required, typically supporting only 1 or 2 workers at a time. It's important to note, as you'd expect, the first 3 slab types are treated as diaphragms and can be analyzed as rigid diaphragms. The metal slab, however, has no structural stiffness contribution and is automatically treated by the software as a flexible diaphragm or as having no diaphragm behavior at all. Therefore, you do not need to manually modify analysis settings when using this type. Below the Slab Type section in the General tab, you'll find Appearance and Material settings for the perspective view. I'll skip over those. In the Geometry section, you can define the slab thickness, the thickness of the metal sheet, and the trapezoidal deck geometry. Since there are many different trapezoidal deck profiles available in practice, there is no predefined library. Instead, you model the deck using these parameters. In the Structural section, we define the material properties. The steel is set as S235, concrete as C30, and rebar as S420. Under Construction Method, you'll see 2 options, shored and unshored. These influence the equations used according to the relevant design codes, so the correct choice must reflect the actual construction method. I'll continue with the unshored option. In the construction block below, you'll see that the checkbox for beam is braced laterally during construction is enabled, which assumes lateral restraint for beams during casting. Now to the Studs section, you can define the diameter, height, and tensile strength of the shear studs. You can also choose the number of studs per rib, typically 1 or 2. This choice depends on the flange width of the supporting steel beam. If the flange is wide enough, 2 studs per rib may be used. For the current section, CHIPE 240, only 1 stud fits per rib, so I'll proceed with 1. In special cases with higher loads or heavy equipment, deeper sections with wider flanges may allow 2 studs per rib, increasing composite action. The spacing between studs is set to 50 cm by default. You can right-click inside the input box to change the units and enter any value you need. Below that, you can see the mesh reinforcement configuration within the slab and define cover thickness as needed. In the Load tab, you can define dead load, live load, and even snow load if you're working on a roof system. For dead load, you can choose from predefined options or define a custom one. The same applies to live load, either select from the built-in library or define your own. I'll click OK and proceed to the modeling. You can model from either the plan view or perspective view. whichever you prefer. I've selected the trapezoidal deck type. For accurate analysis, it's essential that the bottom of the deck profile is perpendicular to the top flange of the secondary beam, ensuring proper shear transfer between steel and concrete. This is critical for the composite action, which relies on shear studs to transfer force through friction between the two materials. To achieve this, I'll select the main beams that run parallel to the decking direction and form a closed area. I'm selecting only the outer frame beams from the plan. I select the final beam and create a closed slab boundary. After that, I right-click, and the slab appears in the perspective view. Let's now confirm what we meant by 90-degree seating. The bottom surface of the trapezoidal deck must be perpendicular to the top flange of the secondary beam. Once verified, the modeling is complete. Now let's create an opening in the slab. I go back to the slab command and click on Draw Slab Hole. I select the slab, then define the boundary for the void by selecting elements. The opening is now created. If I want to delete it, I click on Delete Slab Hole command and I move the mouse cursor near the edge, and it changes. Clicking on the boundary allows me to remove the opening easily. Thanks for watching. Don't forget to like, subscribe, and explore the knowledge base for more tips. See you in the following video.